Hello, I'm Chris Draxler from the RIAVIS Research Center in Vienna, Austria. I present the methods for the efficient simulation of large volumes of rover imagery to train a deep learning system for scientific target selection. This is part of the ongoing MassDL project funded by the Austrian Space Application Program. The goal is to investigate the feasibility of deep learning for autonomous target selection for future rover missions. The full scope of this project is described in Abstract 189 and presented by my colleague Gerhard Paar. The success of deep learning for object and pattern recognition is remarkable. This suggests apply for autonomous target selection of future Martian rover missions. It promises two major benefits. First, such a system would support planetary scientists by detecting and highlighting interesting regions in instrument imagery. This might include features easily overlooked, thereby increasing the overall scientific discoveries. Second, it should speed up mission operation planning by helping to decide where the rover should go next. Deep learning requires a large amount of training data, usually thousands of images. Also, past and ongoing rover missions have provided a wealth of imagery from different regions of Mars. This data is not sufficient for training and also provides no ground truth. For that reason, simulation is required. It is based on an accurate 3D reconstruction of a Martian region, which we call background scene. The 3D terrain models can be viewed from different angles and hence can be used to obtain large volumes of training data. We decided to focus on shatter cones in our study. They are microscopic evidence of shock metamorphisms and formed during meteorite impact events. Shatter cones come in a variety of sizes and shapes, mainly depending on the rock type, but all of them have distinctive fan shape or horsetail structures that show striations. This makes them well-suitable objects to train a deep learning system and assess its detection reliability. The picture above shows co-author Christian Köberl, a geologist and expert on impact structures, studying a shatter cone. The picture below shows a shatter cone from the collection of the Natural History Museum of Vienna. Since we cannot expect to find shatter cones in available digital terrain models of Martian surfaces, our idea was to place 3D models of shatter cones into these scenes, which provide a realistic geologic context. A 3D capturing and reconstruction campaign was undertaken at Natural History Museum in Vienna to obtain several 3D models of shatter cones for that purpose. The picture shows co-author Andreas Bechtold at the capturing setup. Thereby, we took care that the resulting 3D models have sufficient geometric and texture resolution so that characteristic features are preserved. An important aspect of the capturing is to ensure homogeneous lighting to obtain a pure albedo map as texture. This is necessary to shade shatter cone models so that they perfectly blend into the background scene. The image textures of Martian digital terrain models are derived from rover imagery and have pre-baked lighting effects, such as shading, shadows, and specular highlights. They are determined by the sun's direction at capturing time. We need to shade shatter cones from the same illumination direction to simulate consistent images for training. The illumination direction of the background scene is thereby obtained from SPICE. Pro3D is a viewer dedicated to planetary scientists for the virtual exploration and geologic interpretation of high-resolution digital terrain models. Fluid navigation through a detailed geospatial context allows a visual experience close to field investigations. And therefore, Pro3D offers the required functionality to render large volumes of training data with a high degree of realism. In the background, you can see a geologic interpretation of the Shale region in Gale Crater visited by the Curiosity rover. The geologic analysis was carried out by Rob Barnes from Imperial College London. For the simulation of training data, Pro3D was extended to mass-produce images by batch rendering. The diagram on the right-hand side shows the data flow. Pro3D loads a 3D background scene and shatter cone models and places them by randomly generated poses. It then produces large amounts of images, including masks, which are directly used for training. The batch operation of Pro3D is controlled by commandos in a JSON file, which defines viewpoints and various other parameters. Data ingested into Pro3D for a simulation run include the JSON file, shatter cone models as OBJ files, the background scene as ordered point clouds, and command line arguments. Ordered point clouds are a hierarchical data structure used by Pro3D to visualize large geospatial datasets. After loading the background scene, shatter cones are placed into the given viewpoint region by a Halton sequence. Positions are shown as cyan dots in the pictures on the right-hand side. This guarantees an even spatial distribution over the surface. Furthermore, size and rotations of shatter cones are randomly varied within defined ranges. Collisions are detected by intersecting bounding boxes and are avoided. In such a case, one of two colliding shatter cones is removed. An example is given in the picture below, where the object marked in red has to be removed. Shatter cones will also intersect with the surface of the background scene, for which a range of intrusion depths are defined. As shown in the picture, there are sections of the model that should be always above or below the surface. Typically, there is also a side of shatter cones which should not be visible in training images. Otherwise, the deep learning network would be misguided. These are contact surfaces where shatter cones were broken or cut from an outcrop, and they often bear a label when the objects belong to a museum collection. Such sites are defined per vector after reconstructions and are part of the model's metadata. Finally, the realism must be enhanced to achieve suitable images for training which resemble true rover imagery as much as possible. For that, shatter cones are color adjusted to fit to the material properties of the surrounding landscape. They are shaded from the same illumination direction as the background scene. Shadows casted by shatter cones from this direction are also calculated and contribute to the realism of the final rendering. We now demonstrate how ProCD is intuitively used to adjust various parameters for a simulation run. After manually placing a shatter cone, we first perform a color adjustment to match the hues of the background scene. It is also possible and frequently necessary to change brightness and contrast of its texture. Then we turn on lighting, which considers the illumination direction of the background scene obtained from SPICE. A consistent shadow is cast from the shatter cone onto the surrounding surface. The ambient light and the shadow density can be adjusted. We place a coordinate system beside the shatter cone with an axis length of 10 cm to get a sense of the true dimensions. This helps to adjust allowed ranges of random size variations. After some exploration, we settle on a viewpoint and hide the coordinate system. In the next step, we set how many objects should be placed automatically. We adjust geometric parameters such as the size range in percent and rotation intervals in degrees to constrain random variations. The maximum distance from the viewpoint can also be defined, as well as the intrusion depth. Finally, the settings can be exported into a JSON file. And here you can see the exported parameters in the newly generated JSON file. This video shows how 4 additional shatter cones are placed automatically beside the one inserted manually. They all use the settings adjusted before and are evenly placed in the viewport region by a Halton sequence. We can then explore the scene to assess if it is suitable for a production of training images. In batch mode, many such scenes can be created automatically, and from them plenty of images are rendered from different viewpoints, controlled by commands in the JSON file. ProCD also batch renders masks of shatter cones and depth maps of the entire scene with special GPU shaders, as shown by the pictures here. Both types of images further support training of deep learning networks. We presented an efficient method for the simulation of large amounts of training images for deep learning networks that can be used for autonomous target selection in future rover missions. We decided to train the networks to recognize shatter cones because of the distinct surface features. For that, they are automatically placed in an authentic Martian background scene, which is then rendered with a high degree of realism. Currently, we are in the training phase of the deep learning network, and evaluation of the results are expected at the end of the year. Thank you for your interest.